Okay, I've got some data. It's about the length of ostrich eggs. Okay, I've got frequencies, and I need to plot a histogram and comment on the shape of the distribution. So the first thing I need to notice about my categories here is that there are gaps in them. Because these lengths have been rounded to the nearest millimetre, I've got this group ending at 135 and this group starting at 136. So whenever that happens, I need to know that I need to adjust my boundaries. Now, because the data has been rounded to the nearest millimetre, it means that this 135, anything up to a bit more than this, anything up to 135.5, but not including that, would be rounded down to 135. And at the other end of the category, anything above, well, anything of 125.5 or above will actually round up to 126. So where we've got these gaps between categories, normally it's the midpoint of these gaps that we go for. So the next category is going to start where the previous one ends. So it's going to start at 135. So instead of having a gap 135 to 136, I've now got them agreeing at 135. So closing the other gaps like that, 140, 141, they're both going to be 140.5, 140.5. Okay, 145, 146, 145.5, go for the midpoint, 145.5 to 150, 151, it's going to be 150.5, 150.5, and then the end point of this category is going to be 165.5. And now I'm ready to get the widths. Okay, this group may look like 135 minus 126 would be a width of 9, but it's not. The actual true class boundaries we've now worked out are these, so I subtract these. 135.5 minus 125.5 is 10. Okay, 140.5 minus this is 5, this is a 5, this is a 5, and this is a 15. Okay, now frequency density, we're doing this because we have to take the width of the blocks into account, because it's got to be their areas that give me the frequency. So therefore, the formula for frequency density is the frequency divided by the width. So I'm going to do 5 divided by 10, which is 0.5. 7 divided by 5, which is 1.4. The frequency 13 divided by 5 is 2.6. And the frequency 17 divided by 5 is going to be 3.4. And for the last one, 18 divided by 15, okay, it simplifies to 6 over 5, which is 1.2. So now I've got my frequency densities, and I'm ready to put these on some axes. So here are the axes I've chosen. Notice I've got labels on my axes, frequency, density and length, and for the length I also need millimeters. Okay, my frequency density scale must always start from 0. I'm not allowed to truncate this, but for my horizontal axis then it would look ridiculous if I tried to start this scale at 0, so I have truncated this scale. Okay, so I am now going to take the data from the table and transfer it onto here. So notice I've plotted sensible numbers here, 120, 130, 140, even though my class boundaries are funny numbers like 125.5 and 135.5. So I'm going to actually use these values to work out where my blocks start and finish. Okay, and so therefore I'm not going to have them starting and finishing at precisely labelled points on the scale. That's fine, that's normal. Okay, so for my first block, it needs to start at 125.5, end at 135.5, and have a frequency density of 0.5. And here's what that looks like. This is 125.5 here, this is 135.5, and this is 0.5 on the vertical scale. So I'm going to put on the other blocks in the same way. So using these values from the boundaries column and these frequency densities, when I transfer them to the graph, I get a complete graph that looks like this. Okay, zoom out a little bit so you can see what it looks like. Okay. Now this is largely finished. Because of the numbers on the frequency density scale, which is labelled frequency density, then anyone wanting to know what frequency this is could work out the width and multiply by the height of the block and work out the frequency. But it's kind, even though it's not essential, to actually put a key on here that shows how many eggs are represented by a certain area. And if we choose some nice shaped, nice sized region, so that it could be one of the effectively the large squares on the grid, something like this, I can say how many eggs this represents. I have to remember what the scaling was. So one of these large squares is actually worth just 5 on the horizontal axis. This is just for me working out. Okay, but on the vertical axis, one large square is worth 0.5. So a large square in the units I've chosen on my scales is 5 times 0.5. So 5 times 0.5 is 2.5. Okay, so my key is going to look like this. So I don't need the pencil marks I made before. I just need to say the key, this rectangle, means 2.5x. So that gives me a nice visual way of looking at my graph and working out how many roughly eggs each section is worth. The other thing I had to do was comment on the shape of this distribution, or just describe the shape. So I can see that this is not symmetrical. I've got a peak, but the peak is not in the center. Okay, if I'd started with a symmetrical distribution with a central peak, then I can see that it would have been pulled slightly that way. Okay, because the peak is actually slightly to the right of the center, which means it's been pulled towards the low values. So if I'm thinking about skew, I always think about which end is positive, that would be this end. And I think about which end would be negative, that would be this end, and it's been pulled towards the low values very slightly. So this is not this is approximately symmetrical, but I'd describe this as having slight negative skew. So that would be my comment on the shape of the distribution. There is slight negative skew. But it isn't a particularly obvious case of skew. And if you had written approximately symmetrical for this distribution, then I think that's fair enough too.